Okay, we are required to find the volume of the solid of revolution generated by revolving the region bounded by y equals 6, y equals 0, x equals 0, and x equals 4 about the x-axis. The region that is bounded by these lines, when rotated about the x-axis, forms a cylinder that has a radius of 6. Each cross-sectional cut is a circle with a center that lies on the x-axis and has a radius of 6. So the radius of each of these cross-sections is therefore 6 units. Now the area of each cross-section is the area of a circle, which is pi r squared. And since the radius is 6, it's the area rather of each cross-section is pi times 6 squared, or 36 pi. Now the infinite sum of all of these cross-sectional areas between x equals 0 and x equals 4 will give the volume of the solid. The volume of a solid is the area of the base times the height. So the volume of this solid will be the integral from x equals 0 to x equals 4 of pi r squared dx. Pi r squared represents the area of each cross-section, and dx represents the thickness of each cross-section. And the thickness is really height. So the sum of all these thicknesses therefore gives the height of the cylinder. All we have to do now is just evaluate the integral, which gives a volume for the cylinder of 144 pi units cubed. Okay, we have the same problem here, but now we are rotating the solid about the y-axis. Now, since the bounded region is now type 2, the boundaries of integration are the lines y equals 0 and y equals 6. We are also now integrating with respect to y as opposed to with respect to x, as in the previous problem. So the volume is now given by the integral from y equals 0 to y equals 6 of pi r squared dy. The radius of the cylinder is 4 units, so the volume of the cylinder equals 96 pi units cubed. Okay, we're required to find the volume of the solid of revolution generated by revolving the region bound by y equals 2x plus 2 and y equals x squared plus 2 about the x-axis. Before we can set the integral up though, we first need to determine the boundaries of integration, and we do this by finding the point of intersection of the two curves. These 2 points are the points A, 0, 2 and B, 2, 6. When we revolve this region about the x-axis, a washer model is formed. The outer cross-section has a radius equal to 2x plus 2, and the inner one has a radius of x squared plus 2. Now, since we have a type 1 region, the boundaries of integration are the vertical lines x equals 0 and x equals 2. The volume of the solid therefore equals the integral from x equals 0 to x equals 2 of pi times 2x plus 2 all squared minus x squared plus 2 all squared. So we're always subtracting, with the washer model, we're always subtracting the inner radius from the outer radius, rather the square of the inner radius from the square of the outer radius, and that will give you the difference in squared radius multiplied by pi will give you the area of the region between those two cross-sectional cuts. Sketching the region and determining which model you're working with and setting up the integral is really the crux of the problem. So all we need to do now that we've set up the integral, is just evaluate the integral. And that's the easy part. So the volume of this solid is 48 pi over 15 units cubed. Right, we're required to derive a formula for the volume of a sphere with a radius of r. Now, at school level, you must have surely seen and worked with the volume of a sphere. So you know that the volume of a sphere is 4/3 pi r cubed. but it wasn't proven at school level. So that's what we're going to do here, and we're going to use integration to do that. So to find the volume of a sphere, we're going to draw a sphere that's centered at the origin that has a radius of r. We're then going to draw in another radius and then drop a perpendicular from the circumference to the x-axis, thereby forming a right-angled triangle. Now, since we're rotating the region so formed about the x-axis, we have a type 1 region, which means that the boundaries of integration are vertical lines. Each cross-sectional cut rather, has a radius of root r squared minus x squared, which we obtain by using Pythagoras' theorem in this right-angle triangle. Now the area of each cross-section is pi y squared, which equals pi times r squared minus x squared. Now, being a type 1 region, the boundaries of integration are vertical lines, and these vertical lines are the lines x equals r and the line x equals minus r. Okay, because we are cutting cross sections in both hemispheres. Now the integrand is even, which means that we can express the integral from x equals minus r to x equals r as twice the integral from x equals 0 to x equals r of pi times r squared minus x squared dx. All that's left to do now is to evaluate this integral, and doing so gives us a volume of 4/3 power cubed for the sphere, and that's the formula that we all learned at school but never saw proof for. And here it is.